Now we're going to look at the graphs of logarithmic functions. And remember, we can graph log functions because they're the inverses of exponential functions. So remember back to inverses. The relationship between f of x and f inverse is that if f of x has the point a, b on it, for example, then the inverse graph has to have the point b, a. So to generate a log graph, first I can think of its exponential counterpart. So if it's log base a, then I can think of y equals a to the x and figure out my two nice points. So remember, the two nice points on this graph are when you plug in 0 for x, a to the 0 is 1. And when you plug in 1 for x, a to the first is a. So those are the two nice points that we graphed when we first did exponential functions. And there's a horizontal asymptote at y equals 0. So remember, you've got this nice little graph here. You've got a point at 0, 1, and at 1, we hit whatever a is. The graph has a horizontal asymptote, assuming that we have an a value that is not a fraction. The graph kind of increases without bound. Okay, so to graph the inverse function, if I want to graph log base a of x, I can switch my x and y coordinates from above. So I should be able to say this graph has the points, trying to change my color there we go, has the points 1, 0, and has the point a, 1, just flipped those. And if we're trading out x's for y's, instead of y equals 0, it will have x equals 0. So the log base a of x graph has a vertical asymptote at x equals 0, has the point 1, 0 as an x-intercept, and then wherever a is, it has a height of 1. So a logarithmic graph has this type of curvature. Remember that inverse functions are reflections across the diagonal line y equals x. So I don't have these graphed on the same grid, but you can kind of imagine reflecting the green graph across that line would land on the red graph and vice versa. Remember the way inverse functions work as well. The domain of the exponential function, which is all reals, and the range of the exponential function, which is 0 to infinity, those should be flip-flopped or inversed or whatever, however you want to think of it, for the inverse. So if we look at the domain for the inverse function, we'll never hit x equals 0, but we can do anything after 0. And the range, this graph decreases without bound and gradually increases without bound. So yeah, you can see that the domain and range have been switched because these are in fact inverse functions. So when you're graphing log functions, you've got to have at least two nice points, these two, and you've got to sketch in the vertical asymptote. And obviously, if we run through some transformations, that can affect the value of these along with whatever the base number is. Okay, so before transformations, let's just practice this with different base numbers. So you don't have to sketch the exponential every time and flip. I was just showing you where these values came from. So if you kind of forget, go back to exponential, which we're more familiar with, and flip all your points. But otherwise, I'm following this rule right here. Log base 2 of x has the point 1, 0 on it. And it also has the point, instead of a1, it's going to be 2, 1, because 2 is the base number. And no shifts have happened, so we have a vertical asymptote of x equals 0. So if we sketch this in, I'm going to draw in my vertical asymptote first. And then I can plot 1, 0, 2, 1. And those 2 points are not a ton to go off of, so if you want more to go off of, remember you could be picking powers of 2, like log base 2 of 4 is 2. Log base 2 of 8 is 3, but you only have to have the two nice points. And that should be enough to remind you, if you've got this shape memorized, what the graph looks like. All right, so with this graph, again, base number is 5, so we always have the point 1, 0, but now it's going to be 5, 1, and we still have a vertical asymptote at x equals 0. So start by sketching that in. Plot 1, 0, plot 5, 1, and it's supposed to be smooth. It's kind of hard for me to draw these in a smooth way, but this is supposed to be a smooth curve, but it's a lot sharper of a turn there because we drop off so fast. Okay, and last one before we start stretching things around. Remember, this is a common logarithm. The base number is 10 if it's not showing. So we're going to plot 1, 0, and 10, and 10, 1, and we still have x equals 0 as the vertical asymptote. So 1, 0, 10, 1. Again, this is going to be even harder to sketch in a smooth way, but something like that. All right. So what if we go on to some transformations? And what about this natural log x? Remember, natural log x is log base e of x. And we need to remember that e is about equal to 2.718, etc., 181818. So when you're graphing, just about 2.7 is what you can estimate. So we've got the point 1, 0, and E1. And again, we're going to think of that as like 2.7-ish. And we still have x equals 0 as a vertical asymptote. So the natural log of x graph goes through 1, 0, and 2.71. I'm just going to kind of put a point between 2 and 3. Call that good enough. And sketch something like that. All right, now what if we have some extra things happening? So remember, with transformations, we're thinking what's happening on the outside of the function and what's happening on the inside. So there are no parentheses around this x plus 4. That means that the x is inside of the log function, but the plus 4 is a shift up 4. The negative out in front is out in front of the function. So this is going to be an x-axis reflection. But remember, that also just means your points are going to shift to x negative y. And then after that, we're going to go up 4. Okay, so base 3. The original points were 1, 0, 3, 1. Change that so it's x negative y. So still 1, 0. Now it's 3, negative 1. And then you're going to go up 4. All right, so and a vertical asymptote, x equals 0. X equals 0 is unaffected by multiplying y by a negative. And if you shift a vertical line up or down, it's still in the same position, x equals 0. So I like to sketch that in first so I have a good guideline of where I'm going. And then we would be at 1, 0, but we're going to go up 4 to 1, 4. And we would be at 3, negative 1. If you go up 1, 2, 3, 4, you're at 3, 3. And remember, picture this red graph here, but reflect it across the x-axis. So the part that used to be going down along the y-axis is going up. And we kind of have something like this. Okay, and for this one, the minus 5 is on the inside of the function. So this is right 5. The 2 that's out in front is a vertical dilation by a factor of 2. What does that mean? That means that every y value gets multiplied by 2. So we're going to do that first, and then we're going to go right 5. So the original points when it's base 4 are 1, 0, and 4, 1. So first let's do x2, y. So 1, 0 still, and 4, 2. And then all of those are going right 5. Now, x equals 0 is unaffected by the 2y piece, but then when you shift a vertical line to the right 5 units, now it's going to be x equals 5. Okay, so horizontal shifts affect the vertical line. They pull it along with. Because remember, our domain here, you could also think about domain. X needs to be greater than 5. So that should account for the vertical asymptote. Excuse me. Okay, so 1, 0, and then we shift this right 1, 2, 3, 4, 5. And 4, 2, 1, 2, 3, 4, 5. And sketch that in. All right, properties of logarithms. What is the point of properties of logarithms? So there are a couple of things. One, properties of logarithms will help us solve equations. That's the biggest thing. When we're solving equations, being able to condense and expand will help us solve. And then next year in calculus, it's easier. Using our properties will make it, easier to differentiate or take derivatives of. Okay, so that doesn't have to mean much to you now, but you could just write, what's the point for calculus? We'll make calculus easier. For us this year, it's going to help us solve equations where maybe trying to fit something on our graphing calculator would take forever, or maybe we're not allowed to use a graphing calculator. All right, so for all of these properties, let A be a positive real number such that A is not equal to 1, and let N be any real number, and U and V are positive real numbers. Okay, so here's our first product property. So if we have the log base A of two things being multiplied together, let's say U times V, then we can expand that out into the log base A of U plus the log base A of V. And the same property is true for natural logs. Natural log of U times V is equal to natural log of U plus natural log of V. All of these properties are true for natural logs, so I don't think I'm going to write them all out twice, but we just did for the first one. Why is this true? Remember, when you evaluate a logarithm, you're finding the value of an exponent. So we're just saying if we're multiplying two numbers with exponents together, we should be adding the exponents. All right, so you can kind of think of exponent rules to help you remember what these properties are. So multiply means add logarithms. The quotient property, if we have the log base A of U divided by V, then that's equal to the log base A of U minus the log base A of V. This side that we're writing out the plus or the minus, this is called the expanded side. So if we say expand this expression into multiple logarithms, we're saying write it like the right side. Or if we give you something that's already expanded and we say condense into a single logarithm, then that's saying go from the right side to the left side. What's the power property? So if we have the log base A of U to the n power, sorry, my user getting a bit crazy here, of U to the n power. If you raise a power to a power, remember you multiply your exponents. So you can say that's n times the log base A of U. So you can multiply the n out in front. And then finally, the change of base formula. So this is if we have the log base A of U. I can, again, this will help with simplifying problems. And the proof for this is when we kind of get to solving problems, we'll kind of go back and do the proof of this, but for now we're just going to use it. So the log base A of U can be the ratio of the log of U over the log of A, or same ratio with natural logs, the natural log of U over the natural log of A. Again, a proof for this gets into like solving equations, so we will get to that down the road. But these are kind of calculator problems for now, and we'll use them to simplify expressions too. Okay. So those are our properties. Let's use some of them to expand each expression. Simplify if possible. That means if you have the log base a of a number, check to see if you can simplify it to like an actual numerical answer. All right, for every different thing that you should have that many logarithms. So we have a number, we have an x, and we have a y. This should first expand out into 3 logarithms. The log base 4 of 16. I'm multiplying these things together, so plus the log base 4 of x to the third plus the log base 4 of the square root of y. Now, the next part is finishing out the expanding and also simplifying. So take a look at each term. If I have the log of a number, I need to see if I can simplify that without a calculator. So the log base 4 of 16. 4 to what power is 16? That's 2. And then what about the rest of these? Well, if you have an exponent or a root, which is an exponent, inside of your logarithm, then it's not fully expanded. So use that power property that says I can make this plus 3 log base 4 of x. And a square root of y is like a power of 1/2, right? So I'll write that off to the side. Square root of y is y to the 1/2. So that means we could also have plus 1/2 the log base 4 of y. Make sure that you're writing the base number. It's wrong to say that this equals log x, log y. That would be incorrect. It's the base number that matters. These properties are only true, by the way, if the base numbers all match. Okay, number 8. So we're multiplying e to the third and x to the fourth, and then we're dividing by both y squared and z to the fifth. So anything that's being multiplied or anything in the numerator of a fraction is going to get an addition sign. So natural log of e to the third plus natural log of x to the fourth. And then anything that's in the denominator is going to get a subtraction sign, minus natural log of y squared minus natural log of z to the fifth. And that's because you could have said minus parentheses natural log of y squared plus natural log of z to the fifth, but I'm just getting right down to distributing that. Okay, now we have to be on the lookout for these. Natural logs can be easy to overlook. This is something I can simplify. So I said, okay, if you have log base a of a number, simplify it. Okay, well, if you have natural log of e to the something, let's add that to our list, then make sure you simplify it. Natural log of e to the third is 3. And then the rest of these just need their exponents pulled out. Plus 4 natural log x minus 2 natural log y minus 5 natural log z. That's my fully expanded problem. We can also go backwards, use the properties of logarithms to condense each expression. So kind of work backwards. If you had something that is a number out in front, that becomes an exponent as your first step. So log base 3 of square root of x, or you could leave it as x to the 1/2, minus the log base 3 of y to the fourth, plus the log base 3 of z to the 2/3. Remember, that means cube root of z squared. But again, you could leave it z to the 2/3. It does not matter to me. And go back and look at number 8. If a term has a plus sign in front of it, it's in the numerator when you condense. If it has a subtraction sign, it's in the denominator. We have a subtraction sign in the middle, but not at the end here. So this does mean that we're only dividing by the y to the fourth. So this should be a single log base 3. The numerator has square root of x and then cube times cube root of z to the second all over y to the fourth. Now, I would leave my answer like that. If I wanted the x and the z to be underneath the same root, I'd have to get common denominators on their exponents and kind of adjust accordingly. I'm not going to worry about that, though. I would just leave it right like this. Okay, and this one here is our last problem. So this 1/2 gets applied to both of these natural logs. So it's 1/2 natural log of x plus 2 minus 1/2 natural log of x minus 5. The 1/2s become exponents, or I'm going to make them roots. And subtraction means when we put this into a single natural log, it's the square root of x plus 2 over the square root of x minus 5. I don't really want you to rationalize that, but I would like you to recognize that that's the same as the square root of x plus 2 over x minus 5, just because I think that that's probably the form that we would be looking for if this were somehow a multiple choice question. All right, so today we're just practicing using these properties, and the points of these properties, we will then use them to help us in the next section where we start solving these equations. That's it for today.